All right, so we were talking about definite intervals last time. And I want to go over, we talked about using the shortcuts for it. But I want to go over something else like before we actually use that one. This is like 5.5b, just for a quick second. Finishing up the idea of intervals. Idea, not how to do definite intervals, but the idea of it. It's the area. A to B f of x dx is going to represent the net area under the curve. We have a formula for figuring this out, but sometimes the formula doesn't help where common intuition does. The methods in 5.6 work for a lot of problems, but not all. So keeping in mind its net area under the curve, we can take advantage of it. Let me just give you an example. Let's do -3 to 0 this, that should have been square root, not parentheses, square root of 9 minus x squared dx. Now, if you look on that little table, we did have one with the square root set up, but it was in the denominator. And this isn't in the denominator, so it doesn't help us. And I can't just take the square root as is, and a u substitution isn't going to help us. But like 5.6 methods are not helpful here. Not until you go deep down the rabbit hole and learn some complicated shit. But what if I say y equals the square root of 9 minus x squared? Let's try this. Because y is usually a substitution for f of x, so I'm not like, this isn't a big stretch here to call it y. Well, if I squared both sides. Okay, y squared equals 9 minus x squared. And if I add x squared to both sides, I have x squared plus y squared equals 9. What is this? It's a circle. Radius what? Radius 3. Where's it centered? Centered at the origin. Let's draw it. That's not bad for a freehand circle. I'm feeling pretty pleased with myself. Well, the original function was y equals the square root of 9 minus x squared. Y must be greater than or equal to 0 here. Because square root can't end up in a negative number. So we're only looking at the top half. Top half circle. And then our limits of integration. we're -3 to 0. So right here to right here, top half, we are looking at that wedge right there. Can I find the area of that without using the integral? We're looking at a quarter of a circle. Quarter of the area of a circle. 1/4 pi r squared. 1/4 pi 3 squared. So 9/4 pi. Square units, whatever kind of units they are. And if we needed an actual decimal answer, we could get it. So sometimes. If you recognize that if I do some manipulation, I can just solve this a lot easier using common geometry, do it.
Where do you get the -3 from? Just from
The limit.
oh, the limit, okay.
Second place right now. Alright, so that like kind of wraps up 5.5. That was the last important thing in 5.5. Let's hit the methods in 5.6 that we actually care about. Because there's, let's face it, we don't know the area for a lot of geometry things. We can do circles, we can do triangles, we can do rectangles. And we can do parallelograms. There's a formula for parallelograms, trapezoids, but there's not a lot of shapes that work. So this is most often pops up when you're going for circles, because the other shapes are easy to integrate as is. Alright, so 5.6 is called the fundamental theorem of calculus. Sometimes abbreviated FTC. To get there, we're gonna use some stuff there's two parts to it. But I'm gonna start off with something called the mean value theorem for definite integrals. And we're gonna start off with a picture. Let's say f of x is doing some shit like this. So this point right here would be f of a. This point up here would be f of b. Now the area, the integral gives us this area right here. It's gonna give us this area right here. If we had an integral, if we just did it where we looked at the area of f of b. F of b times b minus a is the area of the largest rectangle. And that has too much, right? includes that. If I did the area with f of A. F of A times B minus A, which is the width, is area of the smallest rectangle. Then there must be some point here in the middle, and I don't know where it is. Where C, this will be like. Let's see. That's C right there. This is F of C. F of C. Do that. Where if I did the rectangle right there. F of C times B minus A. It's gotta equal the area of the overall integral. And I don't know where that value is. But it's reasonable to think that there is a rectangle that has the same value. As the area of the fucked up shape. Does that make sense? Does that seem reasonable? Okay, that's graphically what's going on. And they often write the mean value theorem for definite integrals. It's either written like that, or it's written like this. They divide both sides by B minus A. There is an official proof where it's not just a geometric thing. But I think the geometric approach. At least makes it make sense. Make it reasonable before we even get into the proof where you're like, yeah, this is math jargony. I don't know if I like it. We did talk about the min-max theorem. Min-max integrals last week. And we had little m of B minus A. Which in this case was like f of A in my picture. Is less than or equal to a to b of f of x dx. Which is less than or equal to m times b, big M times b minus a. And in my picture, this is like f of b. We had that. If we divide or multiply everything by 1 over b minus a. We get m is less than or equal to our target, 1 over b minus a to b f of x dx. It's less than or equal to m. And the intermediate value theorem applies here. F is continuous, and so. F must attain all values. Between little m and big M. And that means there's a value. F of C is somewhere in there. Such that f of C equals 1 over b minus a to b f of x dx. It doesn't tell us what the value is, it just tells us there's a value that exists somewhere. I think the geometrical approach, the graphical version, to me makes a hell of a lot more sense. This is really a conceptual idea and it's hard to have that concept without an image for me. I don't know about you guys. Point is, there's somewhere in the middle that has the average, that has the value. If we turned it into a rectangle, we would have the area. Alright, so the next the first part of the fundamental theorem of calculus kind of uses a similar idea. Anyone need this up? Oh, Brian still, right? Anyone else? Just wait on you, Brian. How is it? Oh, I'm not rushing you, I was just being jerk. Alright. So FTC part 1. I never remember which one is part 1 and which one is part 2. But we're gonna say let f, little f be a continuous function. And we'll define a new function. Big F. Where big F of x equals the integral from a to x. And we say f of t dt. It's worth noting. Note if x is a specific value. Or fixed value. Then the integral a to x has some value as well. Specific value also. It's an area. So what about f of x plus h minus f of x? This is representing a value. So like, if this is x, well, there's a, there's x. So this is the value f of x. And that's representing some value like a1. And if I go to x plus h, where h is just a small step away. Could be a little bit higher, could be lower. But we'll say it's a little bit higher. We got like that. Well, this value here, this height here is f of x. Because it's based on the right hand endpoint, and this value is f. We're just plugging in x. If I subtract off this box here. Yeah. It's approximately f of x times h. Which would be this box right here. Doesn't go all the way up. It has a width of h. Because x plus h minus x equals h. It's approximately that. For small h. Which means I could divide both sides by h. And I get f of x plus h minus f of x over h is approximately f of x. Does that look like anything that we've done in this course? And if so, what? What do you mean by limit? It's not the definition of a limit. It's the definition of something though. It's the definition of the derivative. If we slapped on a limit as h goes to 0, well, now we've got the definition of the derivative. So this is kind of implying. This implies that the derivative of big F is little f. And so we started with f of x equals a to the x of f of t dt. And we're going to take the derivative of both sides. This turns into f prime of x. This doesn't really change. Because we don't know what t is, can't do anything with it. But we know this should equal f of x. By our implication right here. We'll do a much more formal proof, but this is what the fundamental theorem of calculus is. Often only listed as this right side. But it is handy to recognize that left side as well. Okay, great for the official proof. And for this, I'm going to say A is less than X, which is less than X plus H, which is less than B. Pictorially, that means we've got our endpoints of our integral. And somewhere in here, there's x and there's a small bump x plus h. With the width h. That's f of x. So we need that in place. What we're gonna do is, we're going to apply the definition of the derivative. To f of x. Big f of x. So f prime of x equals the limit as h goes to 0. A big f of x plus h minus f of x over h. And I want that. I'm gonna write what that was over here for a to x f of t dt. So when I do this limit, I'm plugging that in. This is the limit as h goes to 0. I'm gonna pull the 1 over h out front so that I can just make it something like this. If I evaluate this at x plus h, I get the integral from a to x plus h f t dt. That's my f of x plus h. And then I subtract the original, which is just a to x f of t dt. We saw in the rules for integrals last time that we can do the following. I'm gonna leave the first part alone. But if I flip the limit of integration. Put x on bottom and a on top. It changes the sign. That's something we learned last week. And we also saw when we have. Notice these two are now the same. Those are the same a. It's like going from x to a. And then a to x plus h. That's just doing the whole region all together. We can do it all together as x and x plus h. This is the limit as h goes to 0. Of 1 over h. X to x plus h. F of t dt. And we saw. Notice. So this here, this length here is h. Which is effectively like a b minus a. Right? So this is kind of like, this looks like 1 over b minus a. Which is. What we just did, the mean value theorem for definite intervals. This tells us there is. For 1 over h. X to x plus h. F of t dt. That equals f of c somewhere in the middle by that mean value theorem for intervals. So I'm gonna do that, I'm gonna put that in. say limit as h goes to 0 of f of c. What happens as h goes to 0 if I'm going from x to x plus h? Doesn't it just c have to, like c is somewhere in that middle? There's x plus h, c is somewhere in the middle. If h goes to 0, doesn't that force c to go to x? C constantly is in the middle between the two, h gets smaller and smaller and smaller. It's kind of like pushing c down to x. And this is what we were trying to show. That is f prime of x, which is what we started with. I'm still on the screen. Move it down. This is the theorem you will use less. It is handy to know, notice. Well, let me put up what the original description of f prime of x was. From the previous page, f prime of x was d dx of ax f of t dt equals f of x. This is kind of saying the derivative and the integral will wipe each other out. That's a handy idea. Which makes sense. If we take the derivative and then we integrate, we should get right back to where we started. They should cancel each other. Does that make sense? All right, let's do some examples. Let's find dy dx. Yeah. Let's say y equals a to x t cubed plus 1 dt.
So David, you can come back real fast to the other page because my video was like my transmission was blurry, so I wouldn't be able to. I'm gonna just that's it. Thank you.
And I'll set up another one for you guys to work on at the same time.
I took a picture, so it's fine.
Okay. Give you a moment to think about that. I'm kind of curious, does AI show this shit? Getting better at things. Oh, it's curious, cause it sucks at calculus too, it's fucking terrible. Do not rely on AI, it is wrong so fucking often. Which is fine if you can identify when it's wrong. Like I can look at, I use it to check my answer keys on tests because humans make mistakes. But if my answer differs from their answer, I go through both of our answers and see, cause they show how they do it. And it'll do shit like 6 + 3 is 10. That's fucking basic arithmetic, you shouldn't be fucking that up. It did that. Let's see if it does the other one. So this is like big F of X right here. And so if we're taking the derivative. We should get, this is F of T. We should get that evaluated at X. We should get X cubed plus 1. Alright, so this one, I'm gonna move it down. Do it like this. And this is F of X. Our theorem is for like X, not X squared. So what I'm gonna do is I'm gonna say U equals X squared. So this turns into F of U. That's so great. This is the FU integral. And now I'm still doing ddx. On both sides. When I do this and I'm taking the derivative, I'm not, this should be evaluating at F of X, but it's not. So when I do this, I have F prime of U, and by the chain rule, I have a du dx that's missing here. I need to do du dx when I do this. This is gonna be tangent x squared plus x squared. But I need a du dx now. So du dx is 2x. So dy dx, that's what it's gonna be. 2x times tangent of x squared plus x squared. I guess we could clean that up, make it 2x cubed plus 2x tangent x squared. Plus parentheses. So if the limit that you're doing, you're not going to apply this very often. This is the lesser of the two rules. But when you do apply it, if it's not x, you gotta do like a chain rule. And when we originally talked about doing it, this is like writing dy dx equals dy du times du dx. That's the chain rule. Alright, that's the lane theorem, I'll let you write it down, and then we'll do, the fun one, well, the really useful one.
You said this was the one we're not gonna use very much.
I haven't. And the reason why is more often than not, wow, that is not how you spell rule, what the fuck did I just write there? Usually when we have limits of integration. There's no variable in it. There, you're going from one boundary to another, you know what the boundary is. So like this entire thing has a variable and it doesn't pop up. It really just doesn't. And usually when we're doing integrals, we're looking for area. So taking the derivative of it, that also doesn't pop up that often. But we will use it in the next one. Fine, number 2. Anyone need longer? Alright. FTC part 2, the good one. If f is continuous on the closed interval. Continuous. Wow. On the closed interval AB. And f is any antiderivative of little f. On AB as well. Only talking about the interval, same thing. Then. We do the integral from A to B. F of x dx, this is the one I showed you before, equals f of b minus f of a. This middle part here is like saying f prime of x equals f of x. So taking the integral of both sides, we get f of x equals the integral of f of x. Let's do a formal proof of why this works. Let's say, like by FTC part 1. G of x equals a to x f of t dt. And since f, big F, is any antiderivative. It's gotta be some form f of x equals g of x plus c. Some constant of integration, we don't know what it is, that's the only thing that could possibly separate f of x and g of x. Well, if I do f of b minus f of a. I have g of b plus c minus g of a plus c. And we distribute, we've got g of b plus c minus g of a minus c. Which is g of b minus g of a. But now we're gonna use the definition of g of x. This is, we got f of b minus f of a equals g of b is the integral of a to b now of f of t dt. And g of a is a to a of f of t dt. This was one of our rules the other day as well. What does that equal? It equals 0. It's a rectangle with no width. So I end up with f of b minus f of a. Equals a to b. The t here is an arbitrary letter. I can just switch it over to x. If I say x equals t. Dx equals 1 dt, nothing's changing. It's just swapping variables. And let's take a 10-minute break before we do some examples. Let me pause on recording. If you would like to hit resume. All right, so that FTC part 2 was telling us if we want to take the definite integral from a to b of f of x dx, we're going to get f of b minus f of a. So integrate. And you don't have to worry about a plus c for a definite integral on here. And then plug in the boundaries. Let's do from 1 to 5 of 1 over x dx. Ooh. Oh, tricksy. What is the integral of 1 over x? Anthony says, I'm not fucking tricked by you. Natural log of x. And the way you do it, you show a substep showing what you're integrating from. And we make a little line and say what the upper value and the lower value are, like that. I'm expecting to see this on a test, this substep. Then you do this upper one minus plug in the lower one. This does simplify. There's actually 2 different ways to do it. I'll show you the one that is not the intuitive one, but always works. When you have natural log subtracted, it turns into division of them. But that's just natural log of 5. Which tells you natural log of 1 equals 0. If you don't remember natural log of 1 is 0, that's the shorter way to do it. Just going natural log of 1 equals 0 and you're stuck with natural log of 5. But if you didn't recognize that and did division, you're still going to do the same answer. That's fun. All right, let me give you another one. I'll let you guys do it. I don't want to take all your fun. You get K. What happens when we integrate?
X to the 3/7 plus one. You're adding the power to, you're adding one to the power.
Oh, I see what you're
Divided by
saying,
that.
so 3/7 plus 1,
Yeah,
what does that equal?
10/7.
10/7. So we'll have x to the 10/7. Divided by 10/7 or multiplied by the reciprocal. Evaluated from 0 to 1. Oh, what do I do here? Say that again? How do I do that? So, this is easier than you think. 1 to the 10/7 is the 7th root of 1 to the 10th power. Which is the 7th root of 1. Which is 1. Same thing applies with 0. 1 and 0 make the exponential fractional exponents really easy. So that just ends up being 7/10. This ends up being 1 and this is -0. So sometimes there's issues. There can be issues with applying the fundamental theorem of calculus. Let's say we're going from 0 to, I don't know, pi/4, and I have sine of x to the 4th dx. Any ideas? I can't do a u sub, because if I try, if I say u equals x to the 4th. I need to do a du, which would be 4x cubed dx. And I don't have any more x's if I replace that. So that doesn't work. So the problem here is. What's the antiderivative? We have no idea. No clue. So we can't really apply this. As is, you kind of would need to do it graphically and like. Maybe do the endpoint rules or something like that. So solution. Do like the endpoint rule idea. We're not gonna do that. The point is to point out that it doesn't work for everything. What about pi/4 to pi secant squared x dx? Do we have an integral for secant squared x? We do. The integral of secant squared x dx is tangent x. So you kind of want to say tangent of pi minus tangent of pi/4. And this is wrong. Why? What? Anthony, you're usually right. You just gotta speak up. I don't know if you were right, 'cause I didn't hear you on that one. Any ideas? This one's tricky.
Is tangent of pi is also sine of pi over cosine of pi, which is 1/0? Or,
Cosine of pi is -1, so it's 0/-1. That's a good idea. And you're on to something, but it's not quite the right thing. Both secant squared and tangent x are not continuous from pi/4 to pi. And it does require a continuous function. We'll hop over to Desmos and show you. The one that causes the problem you're thinking of with tangent is at pi/2, which is between pi/4 and pi. Tangent of pi/2 is sine of pi/2, which is 1, over cosine of pi/2, which is 0. We have an asymptote there. So these little stagger points are the increments of pi/4. Pi/4 is here, pi/2 is here. Let's just make a line there. Oops. Make it dotted. You can see it's an asymptote. And I'll throw in tangent x. An asymptote for that one. So. We don't have a continuous function over pi/2. For either of these. It's an asymptote for both.
I have a question. How
Yeah.
do you change the numbers into radians?
This,
Yeah.
I did settings and I did step size. I changed step size to say pi over something.
So you just put pi, that's gonna okay.
Yeah, and it'll change it to make it look like radians.
Oh, okay.
Alright, back to our previously. Where's my Zoom thing? There you go. Share, we go back to the other camera. So like it's not continuous there, we can't do it. Alright, let's see, what else we got over here? So how can we think about what this part 2 is showing us? The net change theorem. The net change in a differentiable function. Big F of x. Over the interval AB. Is the integral of its rate of change. Yeah, this is the net change from A to B. I'm gonna write it like this, so it's clear that what f of x is, or the inside is. this is a rate. F prime of X is a rate. It's a like slope, it's a rate. So like different interpretations of this, like in economics. If C of X is the cost of producing X units. Then C prime of X is called the marginal cost. Which is. I believe it's the cost of producing one more unit. I'm not an economics major, so don't quote me on the definition of marginal cost. But it reasonably makes sense. For a rate of change, it's often done as a unit rate. So if we have, like, if we're doing x1 to x2 of c prime of x dx, we're gonna get c of x2 minus c of x1 by this net change thing. It's the cost of increasing production. From x1 to x2. x1 units to x2 units. Because it's like so much to make 5 cars, how much does it cost to make 20 cars? Or how much more does it cost you to make 20 cars? Other examples, this is related to. Somewhat like physics. If V of T. Is the volume of water. In a reservoir. Reservoir. That's a awkward word. At time t. Then V prime of t. Is the rate at which. The overall water level changes. Either by having it, like flowing in. And or flowing out. This matters to companies that sell fish. Certain kinds like freshwater fish, shit like that, they're doing it in tanks. They are not trying to fucking harvest fish from the river to sell a lot of. And like fish in a tank pollute the shit out of the water by shit. So you gotta filter it, but it usually goes into like a filter thing. The water flows in, the shitty water flows in, the filter water flows out. If the water flowing in and the water flowing out are not equal, there's a change in volume. So it matters, they want to keep that at 0. So what does that do? It gives us the volume of water added over. added or subtracted between T1 and T2. Other things that pop up, the more in physics. This shows up in differential equations and stuff. The mass of a rod. Measured from left to right. Then we got some rod, it's just a bar. If it's measured from left to right to a point X. Is m of x, so m is going to represent the mass function. Then the linear density. They use, it goes by the character rho is density. It's like a curvy peak. Rho, it's a Greek letter. P of x is the derivative of the mass. And we got a to b rho x, not p, rho. Rho of x dx equals m of b minus m of a. I don't know how often you're calculating that shit. But it does show up in the right fields if you're going into material engineering, shit like that. Density isn't necessarily a constant function, stuff like that. So depending on what you're doing in engineering, this might be an important topic to you, and it will show up in that class. We got the good old basic one, motion. If an object moves along a linear path. With a position function f of t. Then its velocity. V of t. Did I use F? This is almost always given as S. I don't know why. P is for pressure, so they didn't want to use like the position function with a P. Maybe they just went with the next fucking consonant in the word. I don't know where the S comes from. Might be related to arc length. We use S for arc length and shit like that. V of t is S prime of t. And if we integrate from A to B of B of t, we get S of B minus S of A. And this is the displacement of the particle. Not necessarily distance traveled.
Like the pendulum ends, not how many times it swung back and forth.
Yeah. Kind of like your position function at 6 this morning was probably in your bed. But let's go 4 a.m. I'm sure everyone was in bed at 4 a.m. comparing it to 4 AM yesterday, you had the same position. Your displacement over the last 24 hours was 0. But you have moved. You've gone to school, I assume you got out of bed at some point on Sunday or Monday. It's Tuesday, so Monday you likely had school or something going on. You definitely didn't stay on bed all day, you at least got up to go to the restroom. You know, unless you're shit in the bed. I don't think that's anybody's cup of tea here, so. You gotta move, so the distance you traveled is not necessarily displacement. And with that, we will segue that into section 5.7. Make sure everyone's done writing stuff down. Does anyone need this up longer? Are you good, Megan? I never know if someone's still copying notes or jotting down their interpretations. So 5.7. I don't think we'll finish it, is on rectilinear motion. It is a fucking weird word. And we've talked about it before, we're revisiting it with integration. I wanna say we did this at the end of chapter 3. I wanna say that's what I think. So, if a particle in rectilinear motion. Has position function st. Then its instantaneous velocity. Instantaneous velocity. U P equals S prime of T. Not a period there. And its instantaneous acceleration. We have A of T. Which equals V prime of T. Which is actually S double prime of T. So if it's got function or position S, velocity V and acceleration A, it follows. From these formulas. That we just got done saying one of them, S of T equal V of T dt, the integral of it. And B of T equals the integral of A of T. So we'll do more with this and we're gonna talk about the displacement told distance travel. Let's just give an example real quick though. If velocity equals sine of pi over, not pi over t, but pi t. Along a coordinate line. Find its position function. if S equals 3 at t equals 0. So this is very much like tracking what Jacob was just saying, a pendulum moving back and forth. If we just track its left-right position, you know, a pendulum swings like this. It might swing over like this, all the way over here. But it follows a trig function, and we're just tracking its position horizontally, it's going along a straight line. Yeah, the ball is actually making a curve, but if we're just looking at horizontal position, it's a straight line. We can find that if we integrate b of t. S of t equals the integral of b of t, which is sine of pi t dt. I don't have boundary conditions here, so we're not doing a definite integral. What is the integral of that? Negative cosine. Anything else? Close. It's divided by pi. If we took the derivative, it would be times. If you're not sure, and this is good to point out. If your idea is, I think it's negative pi cosine pi t. Test it. Take the derivative. Taking the derivative of negative pi cosine pi t would give me pi squared sine pi t, which did not get me back to the original value. So this is over pi. What else? We're missing something. Plus C. We didn't do the definite interval, so we didn't have boundaries, we gotta have a constant of integration. So we know we can find C using this. Use to find C. At S t equals 0, this should equal 3. And this equals negative cosine pi times 0 over pi plus C. Oh, that is so ugly. What does that evaluate to? What's cosine of 0? No.
Oh, I know.
It'd be nice if it was 0. It's not 0, this is 1. So if I add 1 over pi to both sides, I get C. C equals 3 plus 1 over pi. Which makes our position function shitty as hell. I'm gonna say negative 1 over pi cosine pi t plus 1 over pi plus 3. Wasn't that fun? You're like, what? Oh, hell no. Now we'll look at displacement versus total distance. And we need this a longer? Okay. So displacement versus total distance. This is like where you were in bed and how far you went yesterday. So the net change theorem actually gives us displacement. Cause that's your net change in place. Net change in position is how far you are from where you started. Started. Let's say you start at T0. And stop at T1. Then the integral of T0 to T1. B of T dt. Gives us S of T1 minus S of T0. Our change in position. Now. This could have some positive motion and some negative motion. So that's positive, that's negative. I could go like this. Then I could come way back over here, have some negative motion. And I could be right back to where I started. So the way we can find total distance. Is adding up these displacements. But like the ones going left. These are adding negative distance. Because it's change of position, so it's taking its. It's taking us back. It's gotta be because all of our positive ones going to the right. If our T0 is right here. And T1 is right here. Then S of T1 equals S of T0. All my plus ones gave positive distance, my negative ones must be giving negative distance. We compensate for the negatives. By absolute value. T0 to T1, absolute value of V of T, dt. So, like the best way to go about showing you, because this isn't a fixed formula for every problem. You have to find the regions of change. And this is easier to do when we have an example, you'd be like, okay, that tracks, that fits. So let's say V of T equals 3t² minus 6t. let's look at when velocity is positive and when it's negative. How can I do that? That'll tell us the maximum velocities and minimum velocities. What's happening when it changes from a negative velocity to a positive velocity?
It goes to.
The velocity's gotta be zero when it changes. Velocity has to equal zero when it changes. So let's do that. Let's set it equal to zero and just like. Find what t's cause this to happen. So if I factor that, it looks like I can pull out a 3t. And I have t minus 2 equals 0. Hopefully everyone remembers how to do this. How do we go about doing this?
The ones on the left equal to 0.
We set both equal to 0. A lot of times people forget it. If there's no parentheses, they leave the 3t alone, but we gotta set them both equal to 0. And we get t equals 0 on this one, and we get t equals 2 on this one. That just tells me when they change signs. How can I figure out when it's negative versus positive? We could make a sign chart. We did this on the graphing stuff. Let's pull out our good old algebra stuff. So maybe I'll test -1, 1, and 3. -1, I will have a negative for 3t. And will have a negative for t minus 2. So the overall region there is positive. If I stick in positive 1 here, 3t, 3 1 times 1 is 3. That's positive. 1 minus 2 is -1, that's negative. This region is negative. And if I stick in 3, I've got 3 times 3 is 9, which is positive. And 3 minus 2 is 1, which is positive also. This region is positive. So v of t is greater than 0. For negative infinity up to -1. In union with 2 to infinity. And v of t is less than 0. Or negative. Not -1, 0. Going up to 0, t equals 0. So let's use this to find, let's find displacement and distance traveled. I don't need A. Find displacement and distance traveled. Between -1 is less than or equal to t is less than or equal to 5. The displacement, we just do the integral. -1 to 5. 3t squared minus 6t. dt. And if I integrate that, what do I get?
T cubed minus. 3t squared plus c.
We don't need a plus c because we're doing the definite interval, but. If you do the plus c, that's fine. Cause if we do t equals -1 to t equals 5, that c is gonna fall out either way. So putting the c in every time isn't gonna hurt you. It just takes a little bit longer. On the definite intervals. So I've got 5 cubed. Minus 3 times 5 squared. Plus c. Minus. -1 cubed. Minus 3 times -1 squared plus c. This is 125 minus 75 plus c. And I've got minus -1 cubed is -1. Minus 3 times -1 squared is -1 squared is +1 times -3 is -3 dot. If I do those first two, and then distribute. I get 54. If we want distance. We are doing -1 to 5. The absolute value of 3t squared minus 6t dt. And this is where we need these regions up here. From -1 to 0, v of t is positive. So I can just use 3t squared minus 6t dt. Remember, the definition of the absolute value of x is it's x if x is greater than or equal to 0. It's -x if x is less than 0. So we can dump the absolute value signs by using that principle here. -1 to 0, it's positive. It's also positive from 2 to 5. But it's negative from 0 to 2. And we can move the negative outside, but I did want to show that's coming from absolute value of the expression. That's the negative region, so we change the sign. We already did those intervals. So this is t cubed minus 3t squared from -1 to 0. Then if I just move the minus outside, I have minus t cubed minus 3t squared from 0 to 2. And then plus t cubed minus 3t squared from 2 to 5. This is 0. No matter what we plug in, we got 0, and then minus t cubed, -1 cubed is -1. But I'll write out the step real quick. Let's see, that value is minus -1 minus 3. So I get an overall +4. And that's just doing part 1. Part 2, from 0 to 2, I'll label these A, B, and C. Trying to do it quick because we're out of time. So this was A. B is gonna go 2 cubed minus 3 times 2 squared. And we're subtracting that. So -8 minus 12. 4 times 3 is 12. That's a -4 on the inside. This ends up being +4 also. That's B. And then C. 5 cubed minus 3, 5 squared. Minus the lower one, t cubed minus 3t 2 squared. We just saw from the last one that this is 4 right there. This is 125 minus 75. So this ends up being 54 right here. That's C. Total distance is adding these up, 62 units. All right, I kept you longer than I should. We're done with that. I will see you guys on Thursday.